Alright, so I hope everyone's doing well in quarantine. So in this video, I'll be going over Faraday and Lenz's law as it relates to induced EMFs and things of that nature. Quite simply, Faraday's law is that the induced EMF will be equal to the change in flux, magnetic flux, of course, with respect to time. So this is basically just saying that if you have a magnetic field, any change in either the field or the area of the region will cause an induced EMF, and then of course Lenz's law is that that induced EMF must be in the opposite direction. If it weren't in the opposite direction, then you would have solved infinite energy problem, because any small change in a magnetic field could induce an EMF, which would then continually just keep growing until you had all the energy you ever needed. So intuitively, of course, it has to be opposite. And now, what's important here is that flux is proportional to your magnetic field times the area. So what really counts here is that what's going to cause an induced EMF is either a change in B field or a change in the area of the region, of the loop, of the circle, of whatever it is you're looking at. So what really counts is looking for either one of those changes. So let's do a quick problem here. So let's say you have a circular B field and you have a loop inside that B field, and let's say the loop is coming out of the page, right? And the B field is a function where you have B naught, which is just some constant, minus CT, where C is a constant and it's a function of time, right? So you have this loop with an inner radius of R and an outer radius that goes to the edge of the B field. Right, here's the B field. It's a vector, like such. Now, let's say we want to calculate the induced EMF. That's usually what an AP question would ask. So we write down our formula here: negative d phi dt. So then what do we have to do? Well, we need to find flux first, right? So flux, like we stated earlier, is going to be equal to BA, right? So here is our B function, right? So let's rewrite that. Oh, sorry, not plus, minus CT, excuse me, times our area, right? Our area of the loop that we care about, right? Circular, pi r squared, right? Because this is the loop with a radius of r, right? And now, if we want to find the induced EMF, we simply take the derivative of this with respect to time. So all we care about is this t right here, because everything else is a constant, and we're integrating with respect to this variable, right? So now we want to take the derivative, and we take the derivative of this whole function, right, of b naught minus ct times pi r squared with respect to time, right? And so this is just a constant, so this just becomes 0, right? And this is multiplied to that, right? So this, when you take the derivative of just your variable to the first power, it just becomes 1. So now you're just going to get negative c pi r squared. And that's going to be equal to our induced EMF, right? So what does this negative mean? What direction would that be? So here we have our function, right? It's decreasing, right? So this is decreasing outwards, out of the page, right? And we know that the induced EMF is going to want to oppose that change. So it's going to want to, in a way, assist the B field, because the B field is decreasing. Right now, if it was increasing, it'd want to go in the opposite direction. But in this case, it's going to go in the same direction, the vector quantity, because it wants to keep the B field where it was originally, right? So because it's decreasing out of the page, our vector is going to want to go out of the page as well. And using our right-hand rule, it's going to be in a counterclockwise direction, right? So it's going to go in the counterclockwise direction. So this negative is basically telling us that our induced EMF is going to cause a current in this loop to travel in the counterclockwise direction. Now, I just talked about current, so let's find current. Well, we know our little equation here, V equals IR, or in this case E, right? Induced EMF, induced electromotive force is basically the same thing as as a voltage. So it's not exactly the same, but for our purpose here, it's the same thing. And so just manipulating this, we get I is going to be equal to negative C pi R squared over R, right? And again, that negative, it's going to be counterclockwise direction, right? And so then let's say it asks you to find the E field. Well, we know the line integral of E dot dl is going to be equal to our negative d phi dt. So to simplify this, it looks scary, but in reality, it's simply just E times 2 pi r, right? Integrate to get E is equal to 2 pi r, and then you're left with this d phi dt, which we found before is negative C pi r squared. So r squared, right? And now we just manipulate, get rid of this r, get rid of this pi, and now we have E is going to be equal to negative C r over 2. In this case, the negative, I guess, really doesn't matter. It's not like we're gonna need that for any other question. And then what's important about this is that this region, this area, right? Because this is gonna be dBA, right? With respect to time, right? So what's important about this is that this area is pi r squared because we care about this area. Now let's say we cared about this entire B field region, right? Our 2 pi r wouldn't change because the E field is still gonna be within this loop, right? So this 2 pi r, this radius is not going to change, but this pi r squared would become pi a squared because the region that we have our B field in, the area of our B field is now pi a squared. So this would go from being C pi r squared to C pi a squared, and then we'd pull over the 2 pi r, and so then we would just be left with CA squared over 2R, right? Oh, that's a 2, not a 3, right? So it's just little important details to think about. And then that's really it. So again, it's important to remember just the simple rule: induced EMF is going to be negative d phi dt, and the negative is just telling us that it's going to have to be in the opposite direction of our change in flux, and that's Lenz's law, and of course the equation itself is Faraday's law. So yep, that's pretty much it.
So today we're going to be looking at the derivation of the ideal transformer equations. So we're going to start off with Faraday's law, since we know that electromagnetic induction happens inside of a transformer. And we know that our EMF induced is going to be equal to negative N d phi dt by Faraday's law, where phi d phi dt, the phi in there is, of course, our magnetic flux, not electric flux, magnetic. So we can define two things. We can define our voltage for our primary coil and our voltage for our secondary coil based off of Faraday's law. We can say one to be negative N P d phi dt, and we can have negative N sub S d phi dt. And what these mean is d phi dt is obviously the rate of change of our magnetic flux, and N is the number of coils in the primary winding, and N sub S is the number of windings in the secondary winding. And they give you the voltage in the primary winding and voltage in the secondary winding. So let's say if we were to find the turns ratio. If we were to find the turns ratio, what we would end up doing is we would end up taking the ratio of V sub P over V sub S. And the thing is, if you divide these two, you'll notice that d phi dt is the same in both of them, So that'll cancel out, and we'll just be, the negatives will cancel out as well. So we'll just be left with N sub P over N sub S. And something very important to note here is that, like, with voltage and the number of turns, they're both, the primary is both in the numerator and secondary is both in the denominator. And then we can actually apply a bit of conservation of energy. And we're actually going to be doing that'll allow us to use conservation of power in this case. Power is equal to IV, and we can say that in this case, I of the primary coil and the voltage of the primary coil equals the current in the secondary coil times the voltage in the secondary coil. And because of this, since since the power is conserved power and I is current, what we can do is we can actually relate this into current. We could say that this is actually equal to I sub S over I sub P. And the important thing to note here is that usually P is in the numerator for voltage and number of turns, but for for current, it's flipped. And that's the ratio, that's like the relationship you need to know between these. And if you want to go a bit further, you could actually use Ohm's law. You could say that, well, you know, V equals IR. So one could then say that R equals, or specifically, R equals voltage in the secondary coil over current in the secondary coil. And what that'll allow you to do is it'll allow you to put resistance in here. But usually you're going to be asked for one of these, the relationship between one of these three, and if anything, you might be asked to know that this is also equal to the square root of inductance in the primary coil over inductance in the secondary coil. And that's like a fun exercise that I can leave for you to do. And one last thing to know is that and this stuff is usually going to be equal to like some constant. I guess you could just call it like C. If C is equal to 1, it's called an isolation transformer. So isolation transformer. If C is going to be greater than 1, then it's a step down transformer. And if C is less than 1, I'm pretty sure you can guess, since C is greater than 1 is called step down, this must be a step up transformer. C is less than 1, where C is, of course, this a ratio that we are seeing here. So this is primarily what you need to know about transformers. So yeah, have a good time studying physics and transformers.